Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. This is a short lecture on how we draw graphs on a torus. Here's a torus. What we want to know is how to draw a graph on a torus. A torus is the surface of a donut, not a solid donut, but just the surface of it, and we want to know how to draw things on it. We don't want to have an actual torus and then draw things on it, but we want to have a representation on the plane. I have another video on tilings of soccer ball where we have done the same thing with a sphere. We took a sphere and flattened it and drew tilings of sphere on a plane. We want to do the same thing here. The question is, how do you make a torus from a rectangular piece of paper? If I have a piece of paper like this, how do I make a torus out of it? And the answer is that you first make a cylinder by gluing the top and the bottom edge. Then you bend this over and glue the two circles to each other. So let me repeat that. You first glue two of the edges of the paper to make a cylinder, and then at the two ends of the cylinders you have two circles, and then you bend the cylinder and glue those, and you will get a torus. You get a donut. So you start with your rectangle, you glue one way, and you get a cylinder, and then you glue the other way, and you get your donut. Now, if you undo that process, if you reverse that process, you go from a torus to a rectangular piece of paper, which is what we want. So let me show you how that's done. So here's your torus. The first thing you do is you cut it across that red circle. You don't cut it like you would cut the usual bagel when you want to make a bagel, but you cut it in this other way. And then you open it up and you get a cylinder. The cylinder has two circles at the end. Those two circles at the end, those two red circles, used to be glued together when we had the torus. So we have to remember that. Now what we do is that we cut this across this blue line across the cylinder, and then we open it up. And when we do that, we will get a rectangular piece of paper. But the thing to remember in this rectangular piece of paper is that top blue line and the bottom blue edge, those two edges are actually the same. The points on those on the torus were actually right on top of each other. They were the same point. And the same thing with the red edges. The two vertical red edges were really the same. So if you want to draw things on a surface, you can draw them on this rectangle with the proviso that you know that every point on the top has a clone at the bottom, that the points on the horizontal blue edge on the top are the same as the ones at the bottom. And we put this little arrow on the top and the bottom to denote that. And likewise, on the vertical edges, every vertex here has a clone, has a friend over on the other side. And I put a double arrow on these to indicate that these two sides are identified. They're really the same point. For example, if you have a point A here, that's actually the same as this point B. These are not two different points. On the rectangle, there are two different points. One is over here, one is over there. But if you think of this as you're drawing on a torus, on the torus, these were actually the same point. The same thing, if C is a point, and these point right above it on the horizontal line above that, then these two are actually the same point. So if you start at A, for example, and draw an edge to the point D, and you can do that, then you can notice that, oh, D is the same as C, and so you can continue the same line without taking your hand off the paper and go, for example, to this point B, but then realize that B was A, and you made a loop. This is not a drawing of two different line segments on a torus, but it's drawing of a loop on a torus. This is how we draw things on a torus. And so the question that we want to know is that, can we draw the complete graph on 5 vertices on a torus? Now, K5 is non-planar. That means that any drawing of K5 on the plane will have edges crossing. And I want to know if I can't draw it on a plane, which also means that I can't draw it on a sphere without edges crossing. If I can't do that, can I draw it on a torus without edges crossing or not? Can we draw a K5 on a torus without any edges crossing? So here's my torus again, and I put with the 5 vertices, 1, 2, 3, 4, and the 5th one, I'll put right in the middle. First, I will connect that middle one to all the other 4, so I don't have to worry about it. That vertex is now adjacent to every other vertex. I now have to connect all the other ones. So first I do this, and what I need to do is connect this top right-hand vertex to the bottom left vertex. But when I do that, if I do that willy-nilly, I might have trapped this top left vertex, which needs to be connected to this bottom right vertex. I start with this bottom one, and instead of going around to the one that I want, I'll go out to the edge. But then I noticed that if I go out the edge, I'm going to come back the other side. And therefore, I can continue my path that way. And this gives me an edge between the bottom left vertex and the top right vertex. And I will do the same trick for the other two vertices. Here I started with the bottom right vertex and went straight down, and notice that, well, I can come up from the top and connect it to the other one. So this is a drawing of a K5 on a torus without any edges crossing. And you can try drawing K6 also and K7 and seeing what would be the first end for which this fails. This is the end of this lecture, but there are related videos. There's one on tiling of soccer balls and planar graphs. There's another one on Euler's formula for planar graphs, another one that uses Euler's formula to come up with a necessary condition for graphs being planar, and this one was drawing of graphs on a torus. Subscribe to my videos if you would like to be subjected to more videos like this, and if you like my video, please like it. Keep hydrated at all times, and I will see you at the next lecture.